Am I audible, everyone?
Yes, audible.
Okay.
Yes, ma'am.
Okay. So in the last session, we have gone through the basic things of computer architecture and computer organization, and we have understood the difference between von Neumann architecture and the Harvard architecture and the pipeline execution, right? So in instruction execution cycle. So what are the different stages involved in the pipeline? What are the different stages involved in the pipeline?
Fetch, decode, execute, addressing, allocating, addressing, and write back.
Okay. So what is mean by fetching?
Uh, Fetching is like reading the instruction, like yeah, fetching the next instruction schedule which need to be executed, which we want to execute.
Okay. So here fetching in the sense it will fetch the instruction, right? So from where the instruction will be fetched?
From
Memory.
the memory.
Okay. Okay. So fetching is nothing but the instruction, whatever it is storing in the memory. So from the memory through the bus connection, so the data will be fetched and it will move to the fetching stage, right? So nothing but the process of moving the instruction from the memory through the bus to the processor is nothing but fetching them. So what is mean by decode?
Executing the fetched instruction has the operand and uh, yeah, it executes the instruction which we got. Like it performs the instruction. Maybe
Yeah.
if it is addition,
Okay. So
so
we
it
have
decodes.
okay some instruction like arithmetic and logical instructions. Suppose some addition or subtraction, some logical instructions like XOR or OR operation. So these are some uh, ALU operations, right? Yeah. So these instructions will be decoded into the system understanding. Okay. So the processor will understand only binary language, right? But as a human being, we cannot understand the binary language. So whatever we want to do some operation, suppose what language as we are human being can understand, normal high level language like A equal to B plus C, like some A is left shift of 5 times, or B is right shift of 5 times, or doing some if else operation. If A is greater than B, then it can perform some operation like A plus B, or else if A is less than B, it can perform A minus B. So this is what we can understand, right? So how we are sending same type of data to the processor? For this purpose, we are taking different type of instructions. Okay. So instruction sets are used in the processor. As we discussed, there are different type of processors like x86 or ARM processor or CISC or RISC, whatever. So every processor have its own instruction set. Okay, like the format. Okay, so the format is different for every instruction set. So whatever we are learning here, that is one type of format. So if you go for some other processors, that would be some other format. Okay. So whatever the operation we want to perform, those operations we are converting into form of a instruction, like add B plus C is there. Sorry, A is equal to B plus C is there. So that is the addition operation. So what can we do? Add the destination register is A is equal comma the B comma C. So B and C are the source registers. By doing the operation of addition, these two data will be stored into the A. Okay. So we are writing this instruction from our human being. Okay. So we can understand both language, high level language and the instruction set like assembly language. Okay. So how the system is understanding same this one. Here add is there. Okay. As per every instruction, like we have different instruction set like immediate instructions, register type or jump type or branch type. Okay. According to that, the binary value will be assigned to the each operation. Okay. Addition have some binary value, subtraction have some binary value, logical operations have some binary value, jump operations have some left shift, right shift. There are so many operations are there. In the coming sessions we are going to learn everything in detail. Okay. So each operation, how we can build the assembly language program for any expressions. So how we can decode that, we are going to learn in the coming session. So today I'm going to cover the basic things of register file, the address mapping, and what are the different type of instructions are there, and how the internal architecture of the processor to the memory communication. Okay, how the processor will be communicate to the memory and what are the internal registers are there. So these are the topics I want to cover today. Okay, so in the next session we are going to cover different types of instruction set. Okay, like immediate type, in immediate type problems we can do, and register type like jump type. So every format will do some problems and we'll try to understand in detail of each instruction set. Okay. So yeah, this is what for this week. So if you observe, each instruction have its own binary value. Okay. Suppose addition means 001. Next, A. A in the sense, it have some register value, right? A is equal to 10, some 10 or 20. So whatever the output we get, that would be converted into the binary value. B and C also converted into the binary value. So that is nothing but decode. Okay. Next, after decoding, execution. Execution in the sense, whatever the result is getting, okay, so it compute the result values or the status and it will store the data into the register or to the memory. So that is the execution step. That means whatever we have decoded the data, that will be sent to the ALU. It will perform the arithmetic and logical operation and it will send to the store and the sent to be memory backstage. Okay. So this is 5-stage pipeline of RISC processor. Did everyone understood the pipeline architecture?
Ashanti, can you please repeat it again?
Which one?
The 5 stage. I understood still like executing after that.
See, in the normal, in common way, I am telling, in commonly, there are fetch, decode, execute, and the store. But in RISC-V, it is a 5-stage pipeline, right? So 5-stage pipeline in the sense fetch, decode, execute, memory, and the write back stage.
Oh, okay, Ashanti.
Yeah, write back stage. So write back stage in the sense we can write into the memory or we can write same data to the register. So both can be done. Okay, did you?
Ma'am,
Yeah, tell.
so how is it affecting different from the general CPU, like memory and write back stage?
How?
How it is creating a different effect and why it is being done in a different way?
Okay, see, data memory in the sense we will particularly store into the memory state. Okay, write back in the sense in the registers we will store. Did you understood? Because from the registers we can again access the instruction for next one.
But for that we have cache already, right?
We have the cache, but cache is different, right? For cache, whatever some in the buffering stage. Okay, so without any delay, the cache data will be used. But storing the data in register is different.
So you're telling about permanently storing in the register.
Yes, yes, we can that would be updated. The permanent value will be updated, but cache is different where we are accessing within some minimum time for cache we use if any data is buffering or any delays is there. For cache, we can use the better use. So this is how these are the 5-stage pipeline in RISC-V. And coming to the how processor and the memory interacting, processor to the memory interaction. So mainly if we observe, we know that only fetching, decoding and execution stage, right? But internal processor, there will be some micro architecture, like how different type of registers are accessing. If you observe here, MBR or MAR, the MDR here, memory address register and memory data register, and how the memory accessing the data here. So here is the memory mapping, the registers R0, R1, R2, and these are the general purpose registers which are used to store the data temporarily, and it will carry the data and it have the values of operands. Okay, so next one is a program counter. Program counter contains the address of next instruction which can be fetched and executed. So program counter is used to fetch the instruction and it execute the instruction according to the level of addressing we are considering. So mainly in RISC-V processor, the data, whatever the memory we are considering, that is sequentially executed memory. So the memory modeling will be there, right? So how we are accessing in terms of sequentially or in order or not. Okay, so a program counter will be fetch the data in a order of memory. So mostly we'll tell like a byte addressing, right? So we will discuss how it is a byte addressing and how it is fetching the data and what are the different ways are there to fetch in the memory access. And next, so another thing is whatever the general purpose register is there, the one of the operand will move to the multiplexer here and it will reach to the control signals and the result will be stored into the JED and it will result will be stored back to the register. So if you observe here the flow, how the instructions are executing, first of all, it will take the data. Here the instructions are available in the memory. From the memory, the instructions are fetched from the program counter. From the program counter to the address register. From address register to the address bus. Whatever the address is sending to the memory through the MAR. From the memory, first the address of the next instruction is transferred to the memory which is located here, and from that the data will be sent to the MDR. It's MDR, memory data register, and then instruction register. So what is the main use of instruction register? What is the main use of instruction register? From instruction register only all the control signals will be generated and the control unit will send the signals to the appropriate devices and it calls the execution of instruction. Okay, so whatever the MPR is getting the data here, the instruction and data will be sending to the ALU here. According to that, the arithmetic and logical operations will be performed. Okay, so from the location, the instruction is copied from the memory to the MDR. So this is the flow of instruction. Everyone understood? Hello. So can anyone tell how actually the memory is communicating with the processor, how the processor is getting the data from the memory? How the processor is getting the data from the memory?
At first, it is getting into the memory buffer register MBR, and then it will go to instruction register set. From there, the respective signals will be sent to the control unit, right, Prashanti?
Yes. And then what is the need of instruction register and the program counter flow of execution?
Instruction register will generate required signals, like control signals.
Okay. Any other answers? Others?
Hello,
Yeah, hello.
hello. Ma'am, instruction register will create control signal. On the basis of that, the data will come from memory to memory buffer register, and the program counter, it will hold the address of next instruction.
Okay. Okay. So any other answers from others? Others, did you understood? So here how the data is, the processor is getting the data from the memory means through the memory bus. Here is the memory bus, right? We can also call data bus and the address bus here, and the control bus is available here. And the program counter will fetch the address of the next instruction. So here the program counter is connected to the instruction and it will get the next instruction, and the program counter will send to MAR. MAR will send to the memory through the address bus. So here the MDR will get the data to the instruction register, and the decode logic will understand what the instruction is here, and the control signal will send the data to the ALU. The control signals are nothing but like a add or sub or any type of instruction. Like according to the instruction, there are different operations, right? The branch operations or some left shift operation, immediate operation, immediate add or immediate XOR, whatever the operations are there, the control signal will send to the arithmetic and logical unit, and in order to carry the operation of these things, according to that, based on the operands, there will be 2 source registers and 1 destination register. The ALU will complete the execution and will send to the memory backstage. Okay, so this is how the processor is getting the data from the memory. Okay, is it clear, everyone?
Yes, ma'am. Yeah.
Okay. So next one, here we are telling like program counter is getting the data in a uh, uh, not in a sequential way. Suppose address is there. Address in the sense 0, 1, 2, 3, 4, like that the address will be having, right, in the memory. But here in the program counter, we are in the RISC-V processor, we are taking a byte addressing. Okay. So why we are taking the byte addressing means here we have the byte ordering model. Okay. So suppose here is the memory. There are n number of locations like 0 or 1, 2, 3. So if one register, one type of instruction is accessing 2 bits, maybe next instruction may access 3 bits, or the next instruction will be started from 4, and the next instruction may started from 6 or 7. So we don't know particularly from which byte the particular instruction is starting. Okay. So for that purpose, what we are doing here, we are taking the alignment for the memory. Okay. So here 2 types of alignments are there: Little Indian format and Big Indian format. Okay. Mostly the RISC-V address space is used byte addressing and Little Indian format. Okay. So there are different processor uses different formats. Like even the most of the other instruction set architectures like x86 and ARM, there are several potentially complex. They having complex addressing modes, right? So RISC-V only uses the this offset addressing with a 12-bit immediate to simplify the load and store units. Okay. So remaining x86 or some CISC, they use the Big Indian format, but here RISC-V using the Little Indian format. Okay. So what is the difference means? If you observe, there is a memory. So in the memory, we are writing some data. So this data is available in the register. Okay. So 956 DAF42. So this data we are writing into the memory locations. While writing into the memory locations, we are considering which, like suppose MSB bit and the LSB bit is there. So LSB bit is writing here in the fourth addressing, fourth location, and AF is writing in 5th location and D in 6th D location. 6D location and 95 in 7th location. Okay, so here it is incrementing 4, 5, 6, 7. It is incrementing. So in Little Indian format, the LSB have minimum and the MSB have maximum. Like LSB have M to MSB M plus N. Okay. So this is how it is accessing the data to store some register to the memory. And whereas in Big Indian format, the register data is storing into the memory. So the 65 is storing into 0 and 73 is storing in first location and second and third location. So here MSB is storing into the 0th location, LSB is storing into the some M plus nth number of locations. Okay. So here you can write here. Here MSB is storing in M plus n location. LSB is storing in M location. Here MSB is storing in M location. LSB is storing in M plus n location. So just a format we are considering. So how efficiently we can use the memory. For that purpose, we are considering this format. Okay. So suppose if you are considering a byte address, suppose if you want to align with a 1 byte or 2 byte, what happens? Suppose a memory is there. So 4-bit alignment will be there, like a 4 byte. Suppose 4 byte in the sense 0, 1, 2, 3, 4, 5. So 4-byte alignment in the sense you can store your instruction at 0th location and next at 4th location and next 8th location and the 16th location. Suppose if you are taking the alignment of 2 byte, then you can store in the 0th location, 2nd location, 4th location, 6th location, 8th location. Okay, 2 bits of difference will be there in terms of byte or bit, whatever the alignment you are considering. Okay, this is how we are storing our instructions in a byte alignment. Okay, so what happens if the memory is not aligned? Can you tell me what happens if memory is not aligned? Hello. Did you understood what I told here, everyone?
Yes, Prashanti.
So for here, we are taking some alignment to store the instruction into the memory. So what happens if memory is not aligned? So directly we are storing in 0, 1, 2, 3 like that. So what would be the limitation of that?
Misleading data, misleading or reading the data wrongly.
Reading the data wrongly.
Like the address or data may be incorrect, which is not expected.
Data will not read wrongly. Uh, Wrong in the sense, whatever the data we are passing, it will read the same. In terms of
There
location, yeah, tell.
there may be some issue in timing closure.
Okay.
I mean, if unalignment happens, then in memory we have to. I mean, memory size will increase now when
Extra
unalignment.
memory.
Yeah. So it leads to timing closure issue.
Memory size will not increase. Within the memory only we use the instruction. Within the memory we store the data, right?
Maybe in case of Little Indian by Big Indian, the LSB will be read first. In case of maybe the MSB will be read first.
Yeah.
In case of
Little
LSB.
Indian format only. We are considering the Little Indian format only in RISC-V. That's why I have taken from 0, 1, 2, 3 like that. So if we won't consider the alignment, so what happens? So instruction 1 is storing here. Instruction 2 is storing here. 3 and 4 may take some more 2 bits or bytes. So next instruction is storing here. So like what would
Loss of data.
loss of data?
Accessing time will be
Um,
more.
There will be no loss of data in this case.
Okay.
Data unidentified. Okay. Okay. So simple reason, what is that mean?
Memory wastage.
Hello.
Memory wasted. Some locations will be unused.
Okay. But
Because of
suppose if we consider if we consider some alignment, then also some locations will be not used, right? We are taking in order, suppose the 2 byte alignment in the sense, any new data will store in the memory like even values, like a 0, 2, 4, 6 like that. Then what about this? Is that wasted?
No.
Will accessing time be more?
Okay, see, if the memory is not aligned, whatever the data is started, it will start at any location. Particularly, we don't know from which location it need to start. We didn't told any, we didn't given any access like it should start from 1 byte, okay, byte alignment or 4-bit alignment. We didn't provided anything, right? So it will be started with any location. So then we need to understand the previous data. So what is the previous data and what is the next data and from which location it have started, because every data is linked. Suppose if we are performing addition plus subtraction, in the sense two type of instructions, two type of operations in same logic, we need to understand the output of suppose, can you connect for the next session quickly, everyone?
Yes.
Using the same link, please connect to the next session.
Yeah.
Okay. See here, suppose we are doing the operation like a plus b of minus c. So here two instructions are there. So a plus b need to perform the add operation. For this result, we are performing subtraction operation with the c. So here dependency is there. So this instruction will be dependent on addition operation. Suppose in the memory, we are storing some instruction in the first location. So it may take some n number of location to store the data. We don't know when the next instruction will be stored, right? In which location it will be stored. We need to check the dependency of before data. So once the addition operation is completed, it will store the data into particular register. That register data we need to confirm, and then we need to check next from which location it have started. Okay. So to avoid that confusion, we need to, without understanding the previous data, whether it is a 1 byte, then if it is 1 byte means next will start from same. If it is some 4 byte means next will be started next other 4 byte, right? So to avoid that confusion, if the memory is already aligned with the number of bytes, like 2 bytes or 4 bytes, we can understand anything that will be started from particular location. Suppose 2 byte means we'll automatically understand the data will be started from 0, 2, 4, 6, 8. So it will be started in those locations only. So we know the possible points and it will be help to know the without any errors. Okay. So for that purpose, the addressing byte, the alignment is very important. Okay. Did you understood everyone?
Yes, ma'am.
Yes.
Okay. So coming to the RISC-V processor, in RISC-V we are telling it's a byte addressing. So byte addressing in the sense the program counter is incrementing +4 to access every instruction. We need to do PC equal to PC +4.
4 is fixed here, or we may change.
Why? Because here in the RISC-V we are using 32-bit addressing mode, right? So for that purpose, we used PC equal to PC plus 4 for 4 byte.
No, ma'am. Can you repeat?
See here, in RISC-V, total, what is the size we are using?
So 32-bit registers.
32
32.
register we are using. 32-bit register in the sense 4 byte.
Yeah, 4 byte.
Right. So 4 byte in the sense every time the program counter is incremented PC equal to PC plus 4.
Okay. So okay. Yeah. Yes, ma'am. So right now the program counter has something. So yeah, currently the program counter might have some address. The address plus 4. So the next address.
Yes. Yes.
Okay.
Okay. So
Okay.
the
Yeah.
program
Yes.
counter will have the current instruction with that particular address. To get the next instruction, so how much increment we need to do? So as it is 32 bit, that means 4 byte. So we'll increment every time 0, 4, 8, 12. So every instruction will be fetched in this way.
Okay.
Okay. Any doubts up to here, others? And always RISC-V uses Little Indian format only from 0 to MSB. So for more understand, if you observe here, we are fetching the instruction. Here program counter is fetching the instruction from the instruction register, right? So every time it will do the +4. When we go to the micro architecture, then you will understand clearly. Some program counter we use the +4. Sometimes in branch or jump instructions we use +2. Okay, for multiple instructions if we use at a time, multiple operations, sometimes we use +4, +2 also. So in the micro architecture, we will observe clearly how to do this and which type of logic can be implemented in a micro architecture level. Okay. So up to here, everyone have doubts? Any doubts? I think up to here it is clear, right? Everyone? So what is the architecture, how the processor is interacting with the memory and the byte addressing, why we are using. And in the RISC-V, why we are using PC equal to PC plus 4. Just now I have told, right? So how it is getting the data. So here is the CPU. In the CPU, we have the program counter and the instruction register. In the instruction register, all the instructions are available. So each instruction size is 4 byte. Okay, 4 byte in the sense 32 bit. So the instructions are available in the memory. So how we are aligning this memory? So this memory having some n number of locations. Okay, 32 number of bits means 2 power 32 number of locations will be there. So in 2 power 32 number of locations, we are suppose if we don't have the alignment, that is very difficult to check the every instruction in the memory location, right? So particularly for that reason, first instruction is I, next instruction is I plus 4, and then I plus 8. That means particular memory address we are storing. Okay, suppose 0th location, 4th location, 8th location, 12th location, like that. Okay, for example, so I plus 12, I plus 16. So every instruction will be fetched in this way and it will be sent to the processor, to the data. Okay, everyone understood?
Ma'am, one question.
Yeah.
So in hardware architecture, we have instruction memory separate and data memory separate, right?
Yes.
So in that case, if here in instruction register, we have this instruction add A, comma
Here in
R0.
memory only, both are separate. in memory, we have both the instruction memory is separate, data memory is separate. Here combinedly, we have mentioned, but both are different.
So let's say the CPU is the instruction register wants one instruction. It is fetching it from the memory. So how does it each instruction is 32 bits, and we are fetching 4 bytes of memory every time an instruction is executed.
Yeah. So here, first of all, how the register alignment will be there. Suppose here is the register and the register is here and memory is here. Okay. So how we are performing any operation? Suppose add R1, comma, R2, comma, R3. So R2, R3 data will be stored in particular register. So R0, R1, R2, R3. So here we'll get the data to the arithmetic and logical unit, and it will be sent to the register. So here the register and memory involvement is there, interfacing. So memory is a 32 bit. So here 0, 4, 8, 12. So in this particular address, the data will be stored separately. The data will be stored in registers actually, R2, R3. Okay, so the data memory is different and address is different. Okay, data is separately storing in the registers. And that registers will be accessed in the memory through the instructions. Okay.
Ma'am, these registers are general purpose registers.
Yeah, general purpose registers. We have the special purpose registers like a program counter and accumulator. So program counter is used for fetching the data, fetching the instruction, and instruction register is there. Instruction register is used to decode the whatever the decoded data is there. That decoded data will be sent to the control register. Okay. So from that control unit, the data will be sent to the ALU. So these registers are involved in the RISC file. So if you observe here, these are general purpose registers. So this is the register file. Here all the general purpose registers. Here is the instruction register which can be sent the instructions to the data to the decoder. Decoder will decode the data, converted into the binary, and through the control unit, ALU will get the data. I mean, control information like what type of instruction, add or sub or jump, whatever. So here is the program counter. These are special purpose registers, and R1, R2, all these are general purpose registers.
Ma'am, data will come in general purpose register from MBR, right?
Yes. Yes.
Okay.
So
On the basis of
register file, all general purpose registers are there in the register file. So register file have the 32 registers. So as we are using 32-bit word here, so 32 registers will be there. So each 32 registers have 32-bit size. But whereas a memory RAM is different. So this is the memory RAM. Memory RAM is going to have the instruction and data. The assembly language program will be converted into the 32-bit. That's called the machine language. And that is going to be stored in the memory. Okay.
Can you go to the other slide, the PC? equal to PC plus 4.
Okay.
Yeah. So here, when we see this instruction, add A comma R0. So now we have R0. R0 is a register, general purpose register. So we need not go to the memory to get that. But A is something which we need to get from memory, right?
That is what here we have the 5 stages in RISC-V. So ALU will perform the both operations. So sometimes we will write the data into the registers and sometimes into the memory. As per our requirement, we can store into the register or we can store into the memory.
Right. So here we need to get right now the requirement is to get the variable A from the memory because we don't have variable A here,
Hmm.
right? So
Variable
what we
A
will
in the
request to
sense,
the memory,
A will have the data. The data will get from the memory.
right? A is a variable which has a data which we need to get from the memory,
Yes.
which is stored in the memory.
Yes.
So now we have R0. So when we request to the memory, what will request to the instruction memory, what will request to the data memory, and how we will get only A. Because when we are requesting to the data memory, we are requesting 4 chunks of memory, right? PC plus 4 brings 4 chunks, 4 bytes of memory.
Yes.
So we want only A. A might be some 1 byte or something, right? In the whole 32 bits.
Okay.
How we will get
Here,
only
first of
A?
all, A is the destination register. So how A will get means once we get the data to the R0, we'll get the data to the register 0. Suppose if there is a register 1 here, for both the addition operation will be performed and that output will be stored into the A. Okay, so how R0, R1 is getting the data in the sense? So already we are storing in the register file only R0, R1 will be there, right? So through that we are storing the data there.
Right. This is for like
Just a
write.
second. Hello. Hello. Yeah, tell. Hello. Yes, tell Rohit.
Yeah. So ma'am, like here that is like writing back to the memory operation. No? Like if we'll consider reading from the memory. Uh, so if we want A is not, A is definitely less than 32 bytes, no ma'am. Less than 32 bits. Less than
Why it is
4
less
bytes.
than 32 bits?
The instruction itself is 4 bytes, right? So A will be less than that, right? Less than 4 bytes.
Okay.
We only want A. We don't want R0 because R0 is already in the CPU.
Okay.
So how it will go and fetch only A? What it will tell to instruction register? I mean, in instruction register, from instruction register, what it will ask, and from data register, what it will ask. I mean, data memory.
So like there is a data in A, whatever the operation have completed, that is storing into the A. So from the memory, what you want to ask?
What we'll ask from the memory if we want only not 4 bytes of data, but only a variable which is less than 4 bytes of data.
Okay. So with this A, do you want to perform any instruction, any operation for the next instruction, suppose add a comma odd 0 is there. Next, in subtraction operation, you want to do some b comma some a immediate of some 10. So here what is happening? A is a dependent here. So A should wait until here it is completed. Then it will be update here. The value will be updated here. So then only it can do the operation, right? So in this case, you want to take only the data from A. Is that a question you are asking?
Yeah, so my question is, so considering any instruction, right, ma'am? So we have here add a comma r0. So here few variables like r0 is already present in the CPU. That is general purpose register. We need not go and ask memory from the data memory. We need not fetch the data. But A is a variable which is not present in the registers. Now we need to get it from the memory. So how does the CPU handle when we have part of the data in the CPU, and we need to get a part of instruction from the data memory?
Okay. See here, two types we will store. Okay, so one is a memory, one is a register. Okay, so if you want to store in the register, we use directly R1, R2 like that. If you want to store into the memory, we use the address of the memory. Like so here 4 is there, 04, 08 memory, 12 memory. So like this we use. Okay, according to that, if you want to suppose load operation we are doing. Load operation in the sense directly we will load some memory data x12 into some 0 into 4. What is the 0 into 4? We are storing the data into some x0 of memory. Okay, so this data will be directly loaded into the x12. Okay, so in the same case, you can take directly from the memory also. That is dependent on our coding style. First of all, suppose expression is there. Wait, I will tell you with the expression. Suppose there is an operation like x is equal to okay. So here so can you tell me what we do first here?
So we need to convert it to instructions level.
Instruction level we need to convert. Okay, so
Right.
how we'll convert into the instruction level?
Yeah, if we'll give this code to the assembler, it will convert into instruction. It might be like add um, uh, add y. We can take temporary variable or something. Add y comma 3 and put it in some temporary variable, and then do the shift operation, something like that, right?
Okay.
It will decode into 2 to 3 uh, instructions.
Okay. Okay. First of all, we will take the register separately. Okay. Suppose to store the 3 value here, 3 is there. Suppose 3 value we are storing into some register or some memory. Like there is into. Okay. I'm taking x0, x8. 8 location or 4th location is there. So this fourth location, we are telling some memory location, we are writing as a x0. Okay, so this value we will take as a in the register wise. We need to load the data, right? First, so we will load the data of some value x10 or some x12. The 0 into 4, we are loading the data. X0 loading the data into the X12. So here next, what we need to load, another register we can consider, and we load the data, whatever we are considering, into some C or 8. Next address is 8 in byte addressing X0 data. Okay, after loading some x0 into 12, x0 into 13, so we are performing the addition operation. So for where we performing the addition operation? Here I am considering it for a B. Y and X. Okay. So immediate operation means we can perform addition I of destination register will be some x25. So here 3 plus y in the sense x12. So x12 comma 3. And next what we need to do, y plus 3 is completed, and then shift left operation of z. So the z will be some register, so it is an unknown value. Here it is a dependent. We are performing z shift left of y plus 3. Y plus 3 is stored in the x25. So the x25, suppose we are considering z data as some here. Suppose this x13, okay, x13 we will consider as a z. And then we can do the immediate operation of shift left, some x25 plus 1, we can consider 26th location. We are storing the data. So which operation we need to do here? Whatever x25 we got, 26, x25, comma, x25 left shift operation of y plus 3, z operation. Z is nothing but x13. Next, what we need to do? OR operation. OR operation of 4. So 4 is the immediate value. Again, we need to use the OR immediate. So OR immediate of, is there any dependent value here?
X26.
X26 is the dependent value. So next value I'm storing into X27. X26 is the dependent value. And immediate value is the 4.
4.
And then next final operation.
Then assigning the value to y.
We assign the value. So,
X27 to y. X.
okay.
Yeah.
So we assign the value to the x directly. So x will consider as x27. Already we have considered. So we are assigning direct value.
Yeah, right now the operation performed completed or with or immediate x27 has the output x.
Just a second. So here we have the word operation. Can you tell me what is mean by X, sorry, SW, anyone?
Save word,
Store word.
store word. Store word.
So here we'll consider the data of X0. Okay, so this is how we are storing the data of final value. So how we are getting the data here from the memory and from the register here. Here register to memory or both are aligned, both are communicating with each other. Okay, so some immediate data we are storing in the memory. From the memory we are accessing, and whatever X or Z are there, those we are getting from the registers. Okay, X25, X26, 27, all these are register internal value. So you will have add some R1 comma R5 R3. So internal values of those are X25, X12. Okay, so within the X25, X12 we have the original data. These are the addresses we are writing. We have the original data. So that is a different part. So which is stored in the memory same. So your question is how we can access, how we will get only this data to the memory, right? So it is in you, if there are some dependent cases, we will access in this way. Is that question you have asked, Rohit?
No, ma'am, that was not my question, but I got clarity now. So basically, when we want only A, the previous instruction would be load word A. So A will have the address where that memory is there, and it will go fetch that data, and then add A comma R0 will be there. I got the answer. Yeah.
Okay. Others, any doubts up to here? Okay. So next thing is, so these are the register mapping. So what are the different type of registers are there, and what is the function of each register? Okay. So like register X0, X1, X2, X3. So these are basically the ABI name is nothing but the pointers. Okay, the stack pointer and these register A and T0, T1. So these are the different type of pointers and the register name, and these are the names for each name. Okay, return address, stack pointer, global pointer, thread pointers. So you can go through the register mapping here. Okay. So before we have seen some instructions, right? Dependencies. So in the dependencies, mostly mostly there will be hazards. Okay. So here while doing the addition operation, the output of addition operation is going to the shift operation. There will be some data hazards and control hazards. Those things we will discuss in the coming sessions. Okay. But before that, very important thing is we need to understand every instruction. We will write some assembly language, and performance also important. Okay, evaluation performance, the CPU performance, those things we'll see. And coming to the type of instructions, you already know what are the different type of instructions are there, right? So arithmetic and logical instructions which execute in ALU, and the data movement instructions are nothing but load and store instructions. Control flow instructions are nothing but jump instructions. Okay, so coming to the arithmetic and logical instructions, so there are integer arithmetic, and we can do the shifting operation, rotating operation, comparing operation, conversion, testing operations, and we can compare with the two operands. Mostly in immediate value, we'll take two operands, right? So in every register or immediate type, wherever we take two operands. Okay. So next thing is the data movement instructions, mostly in the store and load. Store and the load in the sense of the communication between processor to the memory. So we will move the data from memory to the register and register to the memory. Okay, so load in the sense, here load in the sense, the data will be moved from memory to the CPU register. Store in the sense, the data will be moved from CPU registers to the memory. Okay, CPU registers means mostly general purpose registers. Okay, so how the data is moving to the memory to the register, register to the memory. Okay, so if the data is moving from register, CPU register to the memory means that is a storing. Memory to the register means it is a loading the data. Okay, and next control flow instructions are mostly like if else instructions, if else a branch type or there, loop instructions are there, right? So the dependent like halting the program. So dependencies branch type. So these comes under control flow. So we will discuss one by one clearly. You will understand. Okay. So first is a immediate type. So what is mean by immediate type? Any answers? How many of you not understood the session today from starting onwards? How many of you didn't got the like what are the things we have discussed? Everyone understood? Everyone understood? Okay.
Yeah.
Today I will share the assignments also. If you work on assignments, you will get more clarity. Okay. So first coming to the immediate type instruction. So first mostly important thing is the format. Okay. So how the formats are there and how we can write the instruction according to the format. Like if you see the protocols, mostly the protocols have different type of formats, right? So your protocol have its own frame format. I2C have its own frame format, like how many number of bits at the start and stop cycle. So address data. Same here also in instruction. Here also we have the frame formats. So we need to follow in the same way. Okay. First, we'll discuss with the immediate instruction. In immediate instructions, we have the arithmetic, logical, shift, and comparison. Okay. So whatever we are performing addition operation or logical operation and I or I or X or I. So I represents the immediate. Okay. So you can write the notes also, or I already shared the material, right? You can follow the material. So shift left logical immediate and shift right logical immediate and shift right arithmetic immediate. So these are the shift operations and like comparison operations like a less than, like a set less than or a set less than immediate, upper immediate. So these are the different instructions out there for I type. Okay. Can you please join for the next session, everyone? Quickly. Can you please join again with the same link? Okay, so everyone joined, right? So immediate data in the sense, the value we will consider one register plus one immediate value. Okay, so if you see the frame format of immediate addressing, there will be immediate value. First, I will write and show, and then you can follow the material.
जास्त मला एसी सर नाही होत त्यामुळे मला
Can
एसी
you
मी
please
शक्यतो अवॉइड करतो.
असं वाटतं कधी मी जाते ते.
Can you please mute? Okay, see. So first there will be a immediate value, like 11 down to 0 bits, and source register 1, function 3. Function 3 in the sense which type of function, whether it is addition or AND operation or OR operation, XOR, shift left logic or shift right logic, shift right arithmetic, like that. Function 3 will be specifically used. Okay, function 3 have like add means and add means 000, and means 001, or means 010. So at the debugging time, it will take the same value. That same value will be debugged accordingly, and it will send to the control unit. From the control unit, send to the ALU. So ALU will perform that specific operation. Okay. Okay, no problem. Okay, so this is the frame format for instruction, immediate type. If you see a simple example, like there are some source to the destination. If we want to perform some addition operation, A is equal to B plus 2. So how we can perform? A will be stored in some register, some X20. Sorry, that is a destination. Okay, destination register also we can select before only. B is for storing some X4, 2. So how we can write the instruction? Add immediate X20, comma, X4, comma 2. So it directly do the addition operation. Like that, if you want to shift some logical, if you want to use shift logical operation, SLLI, B left shift of 2, and then storing the data in A. Then X20, comma, X4, comma 2. So automatically it will perform the left shift operation, and then XOR operation, XOR I. So these things we can write very easily. But before I have given some expression, right? If you want to write for that expression, that would be difficult. Sometime direct expression also we can write, but there will be some dependencies. Okay, so branch statements also need to write. So that would be somewhat difficult. But while we are practicing, we will get all the things. Okay. Suppose before I have given some example, right? If you want to write in immediate, using the same immediate, what we'll do? We'll send both X or Z into the particular source registers, and we'll select the destination registers, and there will be temporary registers. First, you need to write all these things, and you can build the assembly program. Okay. Suppose X is equal to W and operation of 10, shift right operation of some Z, and we can do some addition operation of some y. So first we need to consider how these within the brackets. First we need to execute, right? So take one temporary register like a T1. Okay, T1 equal to W and operation of 10. Next, take a second temporary register T2 is equal to what we need to do? Left shift, right shift operation of Z. So for which we are doing right shift operation T1. T1 right shift operation of Z. And then finally, both we are doing the addition operation plus y. So plus y in a sense, a is the final destination value. So a is equal to T2 plus y. So T2 plus y. So here if you observe, both are registers, right? Both are registers, but in immediate we cannot do both registers. So you can consider some value here. Okay. If you are using register to register, we can use the both register, but in immediate we cannot use both register. So this is how we need to consider first. Then you need to write the assembly language program. How we can write add I, shift right I, and addition of I. So you can build the assembly language program in this way. Understood, everyone?
Ma'am, there is
Hello.
one, I have one question, like how this format, like instruction format, I type has a IMM of like 12 bits, RS1 function, func3 RD opcode, like if the, for example, I need to perform an instruction add immediate, some destination register, some source register with some constant value. So that is my instruction one. So how can I relate with this format?
Okay. See, instruction immediate value is 11 down to 0. We have the source register here. Source register value will be there. So how many number of bits means mostly bits. Source register will be 6 bits. Function 3 will be 3 bits only. Okay. And destination register also mostly destination register is 8 to 11, 8, 10, 8, 9, 10, 11, and 6, 7. Mostly 6 bit. Destination register also 6 bit. Opcode is 6 bit. Sorry, 7 bit. Okay. So based on that, we can relate. I will show you the table in the next session. Today, I'm just telling the basic things. Okay. So according to that, the values will be converted. The source register, how much size, how much data we are considering. Immediate value in the sense here, like a 10, here 2 we have considered, right? So those are immediate value. So those we can take in that range, total 12-bit range we can consider. Source register 7-bit and the destination register 7-bit. Opcode is a 7-bit, 6 of 7. I need to confirm. So in that way, we need to consider.
So if the program counter fetch an instruction, so the if it is a I-type instruction, so the format will be this exactly
format.
in this format.
Yes.
So the compiler will understand exactly this bit.
Yes. Yes.
I mean the instruction set something.
Suppose here immediate instruction, immediate value is a 10. Okay. So 12 bits. 12 bits, how can we convert into values like 4 zeros, 4 zeros, and 1 0, 1 0. So the 10 will be decoded into this value. Source register 1 is there. In source register 1, we are storing the 5-bit data. Okay, suppose source bit, register, source register 1 is a 5. So we are converting that 5 value. Suppose I'm considering 8-bit size. So 5 will be converted into 0, 1, 0. And function 3. Function 3 is for addition. Suppose we are considering addition operation. Addition operation function 3 is 000. That is 3-bit size. Destination register. Destination register is a size of 7-bit. Suppose that 7-bit will
Okay.
be stored after doing the operation. The data will be stored there, and the opcode. So opcode in the sense whether it is a immediate type or register type or branch type or jump type. Each opcode they have like a 7-bit. Opcode is a 7-bit. So for 001. Suppose for immediate operation it is a 1. So opcode is 1. For register type it is 2. Then opcode is 2. So this binary data, the instruction will be decoded into this format. That's why we are using the decoder. Okay.
Okay, yeah.
After decoding in this way, that value will be sent to the execution stage. In the execution stage, I will show you the circuit diagram. See. So what is happening here? Decoder is there. That actual instruction. So IR is there here. IR. IR in the sense
Yeah.
that have the instruction register, all the instruction format that would be converted into the decoding. The decoding will get this logic. The control unit will get all the details like immediate type or register type or jump type or branch. This information will get, and also the data will get like addition or subtraction, or because every logic, every instruction have addition, arithmetic and logical operations, jump and branch operations. So specifically we'll have the function. So that function will be sent to the ALU. It will perform the operation according to the register datas, and it will send to the destination register.
Yes. Yeah, understood.
Everyone understood? Okay. So everyone understood up to here?
Yes, Prashanti, understood. Did you?
So next one is a OR type. So OR type in the sense register type. So in the register type, before
Hello.
we, hello,
Ma'am, one question.
yes, sir.
What is that meaning of that immediate value? You are using immediate value. What is that meaning?
In the sense, the register immediate, the immediate value we are sending to the register. That means register to register means both values will be stored into the register. Suppose add or 1 or 2 or 3. That means both source values we are storing into the register. There are no immediate value. Immediate value in the sense what? Suppose add register 1, register 2, comma some 10, some immediate value, this 10. Sometimes what happen mean directly sometimes we may need to send some direct value, right? Without storing into the variable, we will send directly some immediate value. Before what I did, suppose a left shift of 2, a right shift of 5. So in this case, what we do, these are the immediate values. Okay, we cannot do the a left shift of B. Even if you do a left shift of B, B should have some value. B should have some value, right? So that's why in some cases we use in this way, right? So that's why immediate value is used.
Okay, so some fixed value is called immediate value.
Yes, yes. Fixed value in the sense direct value. Directly value we are sending without storing in any variable or without storing in register.
Constant,
Constant or
direct,
direct
yeah,
value.
constant value is immediate value.
So constant value if come in that operation, so it will become immediate operation.
Immediate operation.
Immediate type.
Yes.
Okay, got it.
Okay. So next OR type. So R type in the sense register type. So before for instruction register, we have some format, right? Like that in R also we have some format. In R also we have the addition operation, logical operation, shift, and the comparison operation. So here before in immediate what we did add I subtraction we don't have in immediate, like add I or I and I, like that we have written, but here directly add, sub, and operation, or XOR, shift left, shift right, logic, shift arithmetic right, like shift less than U. Okay, so like this we have, but here format, what is the format? First, we have the function 7 format. Function 7 in the sense, what are the function 7 in the sense, we have two type of operations here. Okay, so arithmetic and shift operation. Arithmetic and shift operation will be defined by function 7. Okay, I will show you example, and there will be a source register 1, source register 2, and function 3, and there will be destination register, and there will be opcode. So this is the frame format. So each have a specific data bit size. Function 3 have some 3-bit size, register destination register have some 8-bit, source register some 8 or 7-bit, like that. Okay, so next session I will show you the clear frame format, then you will understand. Okay, so function 7, what is the function 7? As I told, like we have two type of operations here, ALU operation and shift operation. So if you want to define ALU operation, it is a 1. Okay, example. Shift operation means some 1 0. So all addition, subtraction, and or XOR comes under this function 7 1. Remaining all left shift, right shift, less than, greater than, all this comes under function 7 1 0. Okay. In this function 0, again we have subclassifications like addition. Addition in the sense like 0 0 0. Again we have some subtraction in function 1 only. So that would be 0 0 1. Like AND operation 0 1 0. Like OR operation 0 1 1. So these are subclassification in the function 7. Function 3 is the subclassification. Okay, like that in again in shift, like shift left means some 0 0 0 0 1, shift left logic, right logic, and arithmetic 0 1 0, like that. These are the subclassification. Opcode is the immediate type, register type, that is the differentiation. Opcode means. So did you understood everyone up to here? This is a simple way to learn. Okay, like a U type, what is the frame format? This is very simple way to learn. But if you go for directly like this, it would be very confusion. Okay, see, immediate type means there will be one source register, immediate value, and destination register. Here only function 3. But in register type, first one, register type, what are there? Function 7. Here clearly number of bits also mentioned. How many number of bits for registers? S1, function 3, or so clearly mentioned. Like store in the sense immediate value, source register 2, source register 1, immediate 4 down to 0. Like branch type. Okay, we'll discuss all these things in the next session. So try to, I will share you the assignment tomorrow. So try to revise all the concepts, and if you have time, just go through all the instructions once again. So whenever we are discussing, that would be more clarity for you. Okay. If we discuss more also, you will be not able to concentrate much. So do you have any doubts up to here? Everyone? Hello. Rahul, why
I
you
will
Yeah,
are
go.
clear.
drawing from two names? That's why I last week I have removed you.
Oh, okay.
You are asking many times in the group, you are telling me someone removed, but actually I removed because you are joining from two accounts. That's why I removed.
Okay. No, I joined from one account.
Okay, who is another Rahul? Two names are there with Rahul.
And now also there is two names in this session.
Okay, okay, I will check then. So, do you
Hmm.
have any doubts, others? Okay, please go through this up to here. And I already shared the material, right? Please go through the material also. Okay. Okay, then thank you all.
Thank you.
Thank you.
Thanks.
Yeah.
Thank you.